Last time we were talking about beginning with a movie that I recorded to show that spontaneous processes have a well-defined direction, so that it can go one way but not the other. And just by looking at it, it's actually, in most cases, easy to tell what is the correct order of time, what is the correct direction of evolution. So this is essentially to say the direction of time typically in the thermodynamic definitions typically go to a more disordered state. And to quantify those type of discussion, we have the second laws of thermodynamics. That is to say, mathematically, if you want to show this, is to say we define this new concept of entropy, that is a state function that measures a specific number of specific ways in which a thermodynamic system may be arranged. Essentially to say how much different configurations it can be. If there are more configurations towards a particular arrangement, then there's a higher likelihood for that arrangement macroscopically to appear when you measure it. So if we define that way, then we say that for an isolated system, the entropy defined this way will always be increasing over time. Or more specifically, we say when it's larger than zero, it's spontaneous and irreversible type of evolution, type of process, because when you, as soon as you increase the s into it, you can never go back, because over time you never get the negative values. Whenever it increases, it's irreversible. And whenever there's no change, it's just no change, it's reversible in a sense that not changing at the entropy level. But whenever you increase a little bit, it never goes back, because everything has to be always in one direction, and it's spontaneous, irreversible. And with that, we look at the first definition of the microstates, that is, we use as a method to define the entropy. And we say we define this thing called omega to be the number of positions and the momentum available to all particles of the system. And we said that for the gas system, as one example, is to say the larger the volume is, the more different positions is possible for each single molecule, each molecule in our system, and because of that, it's a larger omega. And if we consider each molecule separately, then each molecule has a distribution possibility of different positions that is proportional to V. So for n molecules altogether, it's actually V to the n type of the entire size, that is essentially the space actually in one certain dimension that we need to consider how many arrangements the systems can have. And then for the internal energy, we said it's a little bit more complicated, but roughly speaking, it's still the temperature or the internal energy towards to the end. Essentially, each molecule can be considered separately, more or less, but at the same time, you have some extra factors to take into account of the conversion between energy and velocity, because velocity actually defines the momentum, and that just happens to be the space that later will be shown actually if you take quantum mechanical type of class, that's momentum and the position are the more fundamental basis of the state for a given system. So essentially, this is just one formula to say that this thing does depend on n, and also does depend on V, and also temperature of the internal energy. And then we said, because the dependence of the omega on n, the number of molecules, is nonlinear, it's actually exponential, it's to the n type of dependence. And because of that, if we want the entropy to be an extensive state that is linearly proportional to the number of molecules, you have to take a formula of the log of those type of definition of omega. So it's essentially to say for convenience to be an extensive function to be comparable to all the other thermodynamic quantities like energy, U and H, enthalpy, those type of things. You typically want them to be extensive, and because of that, you have to take a log of omega. And there is just a particular constant to connect those two terms. Today we actually will find out what this particular K is. With that, we look at a particular example that is a gas expansion to vacuum. So we start with a situation where all the molecules are on one side of those two connected vessels, and on the right side of this chamber is empty vacuum. So if you open it, then those molecules will move, a part of them will move from the left to the right. And we say that after you open the valve, it's highly unlikely for the molecules to just randomly, based on the random motion, to entirely move back to the original positions entirely on the left, just by statistically impossible just because of the arrangements that it's very unlikely for the automatic motion of the random motion of the molecule to have all the molecules automatically compressed to the left. And this is essentially because microstates, the omega, is drastically different for those two situations. For this particular type of case, if you open the valve, then you have to double the volume, and you can say that the number of counts of the possible states that can be arranged is essentially 2e to the n, essentially this type of formula. And if you're looking at the one volume, so just half of the entire volume, they actually can be over to the n. So you have those many types of arrangement of possible states. So if you compare those two different ratios, essentially how many fold of increase there is in terms of the microstates now you have after opening the valve, there's a pretty large number of 2 to the n. If the n is considering to be 1 mole, it's 10 to the 23rd, then it's actually a really large number. It's because 2 to that number is truly big. It's impossible at all for the system to sample this much smaller volume in a sense when it actually has an entire volume. Just have no chance to actually ever occupy that much smaller volume of 1/2, but it's actually much smaller likelihood in that sense. And then we say, based on this definition of the entropy, then you can directly rewrite it so that the delta S is equal to the K of this thing, essentially, which is equal to the n times K of log 2. And now, because log 2 is positive, K is a constant that is also positive. So this immediately gives you a delta S that is larger than 0. So it's essentially to say, as a gas system in this expansion thing, you can directly use this definition of entropy to explain why this process happened. Is essentially because the delta S is larger than 0, and because of that, it's a spontaneous process for the gas to expand from this first situation to the second situation, but you cannot go from this situation back to that situation, because in that case, it will be the reverse of the delta S, that is negative 0, smaller than 0. So essentially, you see from this microscopic definition, you can already start to look at different processes. There's a redundancy of discussion, I guess, but you can either follow the omega to say that the omega increased dramatically, or you can say that the delta S increased based on this definition of the log of omega. Both ways are the same explanation for this particular situation. So now today, as I mentioned, we want to look at the entropy from a different angle. The reason is that although the microscopic definition is certainly relevant, and we say that it's already powerful in explaining those type of situations, it's very difficult to use because you don't always want to actually look at the system at the microscopic level to count the molecule and also count the state. As opposed to that, people often just regularly using this type of concept of thermodynamics, they actually work more towards thermal energy, like heat transfer between systems and the amount of work that is being done in a system. And because of that, you try to figure out if there is a way to connect the heat transfer and the work actually to the definition of the entropy. So now, last time we already mentioned this type of thinking experiment essentially is to say, second law says we cannot extract work from a single heat bank without side effects. That is to say, in here, if you started from this single heat bank, essentially a single system, there is no chance that the molecules, the random motion of the molecules in there will be automatically arranged. So they start to move into the one direction, so that can be producing useful work that can, as I said, due to those aligned motion, somehow the system will automatically go up. It just never happens. So this is to say, work is essentially an ordered motion. It's a more ordered structure, it's more structured type of energy, as opposed to the thermal energy that is random motion, that is essentially less structured energy, that is more disordered. It actually has more states that are random than the single state of